Assalamualaikum. Hello everyone. So this is simply a continuation of what we have discussed on limits and derivative. Just get the slides. So this is basically a section on differentials. So just to share with you a more detailed explanations, descriptions of the concept of differentials and the interpretations. So this is just a review where when we talk about derivative of f at x, so technically we are referring to the limit of this difference quotient. So this is the difference quotient because it is the difference between f of x, and when we change x, when we add h, changes to x. In other words, this h is actually an increment, an amount that we have basically increased x by a small amount h, where h approaches zero by a very small amount. So this is basically the technical definition of derivative. Okay, of derivative. Why we want to use increment notation? Because increment notation, later on you'll be introduced to this increment notation. It allows us to interpret the numerator and the denominator of the difference quotient separately. In other words, we can uh, interpret the meaning of the numerator and the denominator differently, separately. Example 1. So we're going to start with this simple example. Well, let's say we have this function that explains the relationship between input x and output f of x, y. So f of x equals x to the power of 3. And let's say we want to focus our attention to the change in x. So remember, what is our x? X is basically our input. Okay? It can be number of workers or hours of studying. So let's say we want to change that from 2 to 2.1. So when we change x, so when x changes, it increase basically from 2 to 2.1. So this corresponds. So what happens to y? So y would change from 8 to 9.261. We simply substitute x with 2.1. Okay. Now, so the increment notation, so the change in x, where x has increased from 2 to 2.1, is denoted by delta x. Okay, delta x. The Greek letter delta in mathematics, so this is the uppercase delta. It is used to represent the difference or change. So when it is combined with x, delta x means the difference or change in x. How much has x changed? In our example, x has increased or changed by, what is the change here? 0.1. It has gone up by 0.1. While the change in y is denoted by delta y. Okay, in our example, so the change in delta x equals to 0.1, while delta y, the change in y, equals 1.261. Our y has increased from 8 to 9.261. So 1.261 change in y, delta y and delta x. So now we can simplify our difference quotient, where we are comparing the changes between x1 and x2. What is x1? x1 is, in our example, this is 2 and this is 2.1. So it changed by a small amount, h, which is 0.1. So this is delta x. This is basically the change in x, which is h, we can be represented by delta x. While the numerator is basically the difference between the outputs. So f of x1 and f of x1 plus delta x. So this is basically delta delta y, the change in y. Okay, so where h equals to delta x. So for y equals f of x, delta x equals x2 minus x1. So what is the value of x2? The new value of x2 will be x1 plus the change in x. And while the difference in y, delta y, equals to y2 minus y1, the original value of y1, okay, and we compare it with the new value of y, which is y2. Okay. So graphically, so pay attention to this example. So let's say we have, this is the relationship, okay, of the function y equals f of x, the blue line. So what we are interested in the differential. So this is basically the difference quotient. When x changes from x1 to x2, so x has increased from x1 to x2 by delta x. So this is the change in x. So similar, correspondingly, y would also change, okay, or f of x will also change from fx1 to fx2. In our example, it has gone up. So this is basically delta y, where delta y equals fx2 minus fxy. Okay. Now, delta x can either be positive or negative. The change can be moving to the right or moving to the left. X can go up or down, while the change in y represent the corresponding change in y with respect to delta x, change in x. So delta y over delta x, so this basically is the difference quotient. The difference quotient, okay, that we used to define the concept of derivative previously. Okay? And this actually gives us the slope of the second line. If we were to draw a straight line here that connect these 2 points, okay, we take delta y divided by delta x, it will give us the slope of this red line. Slope of the second line, the straight line that connects these 2 points. Okay. This is a second example. Okay, if you would, I'm going to leave this example to you. You can just go through it on your own because I believe it is simple enough. So if this is basically a change when we increase x1 by one unit from x1 to x2, from 1 to 2. So the change in x equals 1, right? Should be very easy, very simple. Why don't we just, since it is simple, why don't we just do it together? Second, now we need to find delta y. So given, so what is delta y? So delta y basically equals to, so f of 2 minus f of y. So what is f of 2? F of 2 is 2 squared divided by 2 minus 1 squared divided by 2 equals 4 over 2 minus 1 over 2 divides 3 over 2. Okay? So what is delta y over delta x? So delta y x equals 3 over 2 divided by 1, which is 3 over 2. Okay? So what is the meaning of this? So the meaning of this, how do we interpret this? This means that if x changes by 1 unit, so y will change by 3 over 2. Okay? So next would be, how do we find this? The difference quotient. The difference quotient. So from previous example, from part A, we already know that so we already know that the, the, the change. Uh, so let's say this is from we are given this information, x1 equals 1 and delta x equals 2. So for this difference quotient, we simply substitute. All these values back here. So x1 equals 1, put it here. This one we put it here. So once we got the value, you simply plug it in back here. Okay. I think it's okay to leave this example to you. Okay? You just go through it and make sure you know how to interpret, okay, the meaning of this last value. Okay? Next would be to discuss this concept of differentials. Okay, suppose that the limit of this derivative, the limit of the derivative exists. Okay, where the change in y with respect to change in x, when the change in x is very small, it exists. Okay? For a small change in x, when x is extremely small, this value, this value can be basically approximated by delta y over delta x. Okay? And because of this relationship, the change in y can be approximated by the change in x multiplied with the derivative, f prime of x. Okay, f prime of x. Now, the differential, okay, where we replace delta with d. Okay, dy equals f prime of x multiplied with delta x, or df equals f prime of x multiplied with delta x. So this is what we term as the differential. The differential. So this brings us to this definition. If we have a function which is differentiable, then the differential dy, okay, or df is defined as the production of f prime of x and dx, where dx equals delta x. Now, dx would be exactly the same as delta x, the change in x. Okay? It is just that dy, the differential dy, will be a good approximation of delta y, of the change in y, provided that delta x, the change in x, is very small. Okay, this all sounds a bit technical, but I hope the example later on would be, would clarify things easily. Okay, so let's just try to understand the concept graphically. Okay, graphically. So previously, what we did is that when we solve, so this is the change in x, delta x. If x were to change by delta x, okay, x has gone up by delta x. So we have these 2 points. Originally, we are here, okay, at x, and then we move on. So our x value has changed by delta x. So this is our new point. We are here now. Okay, we are here now. So we are interested to know what would happen to our f of x. How much will our output or our dependent variable change? So we want to know the change in y. So based on this, if we look here at this point, now this blue line, this blue curve is our original function. Our original function. Okay, it is just that usually in business, okay, in economics, in normal life, the actual or the precise relationship is usually unknown. Okay, it's unknown. But if let's say it is known, then we can easily know that delta y would change by this amount. Y will go up by this amount, right? Because it is here. Okay, this is delta y, changing y. Okay. Now, these 2 points are connected by the green line, the second line. So delta y divided by delta x. So what is this? This will give us the slope of the second line. Okay, the second line, the green line, the actual line, that the line that connect 2 actual points on the original blue line. Okay. Now, when we want to apply the concept of differentials, so what we are doing is that, so what if we make the change in x to be smaller? Now, when we make the change in x to be smaller, okay, the change in x to be smaller, so what would happen is that we are moving it. Okay, we are moving the second line further and further to be nearer to the original change x, right? As we make delta x smaller, so basically we are moving back to the left. Now, as we move back to the left, so the line gonna be flatter and flatter. So as you can see here, Now, we are using the concept of differential. Look at this tangent line. At this point, we have this red line, which is a tangent line. Now, this tangent line, okay, the change where the change in y is measured by this relatively shorter, right? This is taller. Delta y is taller than dy. But dy would be a good approximate of delta y, provided that the change in x is small. Okay, so the tangent line, okay, would have the slope of f prime of x with horizontal change dx. Okay, so that would be the slope. F prime of x would be the slope of the tangent line. Okay, so the vertical change is given by dy. Dy. Okay. So how do we find dy? So we can find dy if we know the slope of the tangent line as well as the changing in x. Okay, so we simply multiply the slope, okay, of this tangent line and the changing x. Then we can get the length of this distance, dy. Okay. So let's see the interpretation. Now, delta x and dx both represent change or actual change in x, okay, the real change in x. While for y, it is a bit complicated. Now, delta y represent the actual change that in y that correspond to change in x, while the differential dy stands for the approximate change in y, estimated by using this derivative. So we're going to apply this derivative. Delta y can be approximated by dy, where dy can be found when we simply multiply the derivative or the slope of the tangent line with the change in x. Okay, so in application, we simply use dy to estimate delta y. Okay, to estimate this delta y. Let's say we have this example. We have this function f of x equals x squared plus 3x, and evaluate dy for x2, for x equals 2 and dx equals 0.1. This is similar to the previous example where our x changed from 2 to 2.1. So the change. So we know that delta x would be equals to dx equals to 0.1. So now we want to find dy. Dy. Okay, so from the previous formula, the previous relationship, we know this is the relationship. So how do we find dy? So we simply multiply f prime of x. So what is f prime of x? So based on this, we simply use the shortcut formulas. This gives us 2x plus 3. Okay, 2x plus 3. So we have dy equals 2x plus 3 multiplied with dx. Okay, dx. So this equals to x plus 3 multiplied with 0.1. So this is our dy. Okay. Now, for x equals 2 and dx equals 0.1, so what do we need to do? We simply replace this 2 with this x with 2. Okay. So we will get 0.7. So this is dy, which is the approximate change in y when x changes by 0.1. When x change by 0.1, basically we approximate, y will change approximately by 0.7. Okay, 0.7. So let's have this example. Hopefully would be clarify a lot of things. So let's say we want to compare the increments and differentials, delta y and dy. We want to compare these two. So let's say we have this function 6x minus x squared. So we want to find delta y and dy. So let's say we want to compare these two. So how do we find dy previously? Equals f prime of x multiplied with dx. So how do we find f prime of x? From this example, f prime of x equals, so we have 6 minus 2x. Okay, and now we have x equals 2. So we substitute this. Okay, so don't forget dx. So when we want to, so okay, the solution basically solve for delta y first. So how do we find delta y? Delta y is simply given by this equation. Okay, this is simply f of x plus delta x minus f of x. Okay. So when we have this, we can basically replace. Okay, so these values into this function. So we're going to have what? So this one, we're going to have 6. Okay, so replace x with these values. So we're going to have this. So replace x with 2 plus delta x. Okay, and then we have minus x squared. Have 2 plus delta x squared. Okay, and then this would be the first term, right? And then minus x squared. So how do I get the, how do I get this f of 2? So we're going to get 2, this one, yes, 2 squared. Okay. So now expand this. I'm going to leave this, how do you going to expand it? So on your own, so you're going to have something like this. So after you have simplified, you have expanded this, you should get this. Okay. And finally, this would be the change or the increments in y or delta y. Okay, delta y. Now, since f prime of x equals 6 minus 2x, so f prime of 2 equals 2, and dx equal to delta x, and then we can simply find that dy equals to 2 delta x. Okay, so from here, when we want to change, we want to analyze at 2, so we simply replace this. So plug this in, okay, to here, so we're going to get, so f of x equals to 6 minus 2 multiplied by 2 is 4, and then we have dx, and this will give us 2 dx, okay, which equals to 2 delta x. Okay. Now, can you see the difference between delta y? So this is delta y and dy, these two. Compare these two. Okay. You can see that delta y would have this additional term, minus delta x squared. Now, this is the actual change in y. Actual change in y. While when we approximate it with the differential dy, this term, the minus delta x squared, is no longer there. It's no longer there. Now, if this delta x, so this is why dy would be a good approximate of delta y if delta x, okay, approaches 0. It's very small. Because when this is very small, then delta y and dy would be not that different. More or less it will be the same. Okay. Now let's say we want to plug in values. So these three values, 0 0.1, 0 0.2, and 0 0.3. Which one is nearer to, which one is smaller? This one is smaller, right? This is basically nearer to, so 0 0.1. This is nearer to 0. In other words, smaller. Okay? And this is bigger. Right? 0 0.3 is bigger than 0 0.1. Now let's say, so what do we need to do? We simply come up with a table. Okay, come up with a table. So this is delta x, okay, which equals to dx. So when x changes by 0 0.3, by 0 0.2, and 0 0.1. Now what is delta y? So delta y, previously if you remember from previous slides, delta y equals, what is it? Right, 2 delta x minus delta x squared from this equation, right? So what we need to do is you simply substitute all these delta x with the corresponding value, and you should get delta y. While dy is simply 2 delta x, right? So 2 multiplied with 0 0.3 will give you 0 0.6. 2 multiplied with 0 0.3 will give you 0 0.6, but then you have to subtract 0 0.09, because 0 0.3 square is 0 0.09, so you get 0 0.551. Now, if you look into this table, between these two columns, compare these two columns. As we make the number smaller, as we make the change in x to be smaller, now dy would become a better approximate, right? Better approximate for the actual change in y. Okay, as delta x becomes smaller, right? So this becomes the differential would be a good approximate of delta y. Okay, so this is this example. I'm gonna leave this to you. Okay, so make sure you are able to do this on your own. So that's basically explain um, the concept of differential. Okay, I hope now you have a clear understanding of this concept of differential, how we apply the concept of limit, okay, into a derivative, and how a differential would be a good approximate to the actual change. Okay, so that's all for today. Inshallah, see you next time. Assalamualaikum warahmatullahi wabarakatuh.